Morning, ladies and gentlemen. Topic for today is A/B testing, which is a method widely used in web data analytics. And that feels like it's a very modern thing, but statisticians have been doing it for decades. Before we get to that, some quick announcements. This is a very unusual week. Just lecture today and then nothing until we see you again on Monday. So, office hours. So there's a project checkpoint tomorrow, and the final deadline's Tuesday after break. The current homework has deadlines that you already know about, and there are office hours this afternoon and tomorrow, and I have my usual Monday, Tuesday office hours as well. Any logistical administrative questions at all? Kernel behaving itself? There are fewer RIP kernel posts on Piazza, so we hope that you're going to be okay. Now, I have asked the GSIs, and they have kindly agreed to watch Piazza over the break occasionally. They won't be glued to it. It's their break as well, but they will watch. So go ahead and post if you have questions. All right. So what I'd like to do is just step back from detail a little bit and look at what we've been doing for the past 10 days or so. And that's mainly been looking at the relation between some attributes, some properties of an individual, and a class into which we can place them. And the class is either heads or tails, or yes, no, right? So the questions have all been, in various forms, the questions have been to do with what's the relation between these properties of the individual and the class of the individual. And this crops up and has cropped up in many different scenarios, not just classification, but just you have two groups of people. And so the typical situation in web marketing is, you go on to a website and you're trying to buy something and you see a page. What you don't know is that behind the scenes, somebody may be treating you as a laboratory animal, right? They might be experimenting on you. So what happens is people, when they are trying to see whether a page works, and a page working means you see the page and then you click on the thing that they want you to buy. Then exactly how the page looks makes a difference, right? Is it easy to find the thing to click on? Does it make it look enticing? And so on and so forth. So frequently what is happening behind the scenes is there's an experiment going on, and you click on this website and you see a page, but it is possible that somebody else clicking on the same website actually sees a different page. And the experiment is to decide whether the particular page that the person sees influences their behavior. And so now you have two samples, and we're going to pretend that for now that they are taken at random, though sometimes they need not be. So you have sample A and sample B, and that very unimaginatively is why the technique is called A/B testing. And the question is, does it make a difference which page you see? And so as statisticians, you know that you will make a null hypothesis. No, it does not make a difference. If you see any difference in the results, that's due to randomness in who got to see which page. Yep. So there's the no, it doesn't make any difference, null hypothesis. Yes, it makes a difference, alternative hypothesis. And now you are trying to decide. So formally, we might say that you have two samples, the A sample and the B sample. The null hypothesis would say they are drawn from the same underlying distribution, and the alternative would say no, they're not. And the process of making that decision, which of those two hypotheses is better supported by the data, that process is called A/B testing. Now, we have done examples that just sort of skirt around this for quite some time. Do you remember our jury selection examples? Yes? So we had an eligible population of jurors, and then we had panels of jurors. And the question was, does the panel of jurors look like a random sample from the eligible population? You recall this? So there also the question was, are two distributions the same apart from randomness? But there's a fundamental difference between that situation and what we have here. In that situation, the distribution of eligible jurors was known. It was known based on census data or something like that, right? So that one was fixed, and the question was, do the panels look like a random sample from that fixed thing? And therefore, we could answer that question by simply drawing from that fixed thing and figuring out whether those look like our panels or not. The question here is slightly different. In this case, both distributions are the result of randomness. Yes, both of them are samples. So unlike our previous example, you can't take one of them as fixed and just draw from that, because both of them have the same status. And therefore, we need a slightly different technique. We need to start out differently. But then once we are set up, we will do exactly the same calculation that we did before. And so the summary of what I've just said for the last 2 or 3 minutes is that our jury selection example, the eligible population was fixed, and it was only the sample that was random. Now what we are doing is both of the distributions are from samples. But we're still asking the same question, are the two underlying distributions the same or not? Okay. All right, so we have hypotheses, which can be variously stated. I will let you read those for a little bit. So we've talked through them already. So you got two random samples. The two samples are drawn from the same distribution. Another way of saying that is they look like random draws from the same set. And for that second way of looking at things, please remember our deflate gate example. We had 15 footballs, 11 of which were Patriots balls and 4 of which were Colts. And there was some numerical measure that we had on all of them. And the question was, do those measures just look the same in both cases? And looking the same was defined as, do the two groups look like random samples from the same set? Yep? Yes? Good question. So the question is, do we sample with replacement or without replacement? Can anybody remind me what we did in the case of the footballs? We had 15 footballs. What did we do? Any memories? Okay, so what I'm going to suggest that you do, you can try either, but it is easier to understand the following, I think, in your head, which is that if the 15 footballs all came from the same distribution, then any permutation of them should be equally likely. So any 11 you can assign to the Patriots and any 4 to the Colts. And you should have the same distribution either way. So I believe if you go back and check, we actually sampled without replacement. We permuted, we shuffled, all 15. Under the null hypothesis, you should be able to shuffle, because the null hypothesis says they're all draws from the same distribution. Another place where we had this kind of idea was, do you remember when we chose the training set and the test set for classification? So we had our original data where we knew all the classes. How did we choose the training and test set? We shuffled, right? And we took the first half for training and the second half for test. It's exactly the same idea. So that was an important question, and by the end of this lecture, I hope I'll show you a place where you would actually sample with replacement. You would bootstrap. But right now, we're doing what are called permutations, rearrangement. A permutation is just a rearrangement. So a permutation test does the following. The null hypothesis is something that I have said about 10 times now. The null hypothesis, you've got two samples, and they're both from the same underlying distribution. And the idea is that if the null is true, then you can rearrange the sample however you wish. Which one you're calling class 1 and which one you're calling class 0 shouldn't matter. So what you do is you compute your observed test statistic, and for this you need to figure out what your test statistic is. And for that will depend on what your hypotheses are, and we're going to spend some time today figuring out what they should be. You first figure out your test statistic, you calculate it for your actual samples, and then you shuffle. You shuffle, you get a new pair, sample A, sample B. You calculate your statistic again, right? Redo. Shuffle again. You get yet another new sample, A and B. Calculate your statistic again, and then you will get 1 million statistics computed under the null hypothesis. You will draw the histogram of those. You have your original one that you calculated first. You compare the two, and you make a decision. Yes? Standard test of hypotheses that we have done before. So what we're going to do is we're going to do a demo. And actually, we're going to do 2 demos. The issue here, the test you kind of know how to do. The issue here is what is the test statistic that you choose. And remember what the hypotheses are. The hypotheses are you are drawing from the same underlying distribution or you are not. Right? Now, here you have to visualize the distribution. What's the distribution? And the example that we were doing at the end of last time's lecture was the distribution was actually categorical. These were ratings on something, right? And so you should imagine the distribution to be a distribution of, favorite movies, if you like. There are 5 movies, and so they're not numerical, right? In that case, you have one categorical distribution and another categorical distribution. The natural thing is to compare the bar graphs. Yes? And what's a number that compares 2 bar graphs? 2 bar graphs would have the same possible values. What's a number that compares the 2? TVD, total variation distance. Right? So that is a natural statistic when you are looking at 2 categorical distributions. And so what I'd like to do is I'd like to go back to that example that we were doing and go through it a little more carefully, and then move to in what situation you do use a different statistic, and so on. All right, so questions thus far? Let's go to a demo, and that will probably throw up some questions that you have. So, okay, so import. We'll use our cancer data that we had, and you will recall that these are various measurements on the tissue that was collected by a fine needle aspiration, and all of these, while they look like numbers, they're really categorical. All of these are qualitative ratings that were given. And so we are going to focus on one of them, which is the amount of mitotic activity, the mitosis. I have relabeled the cells, the classes not cancer and cancer, just so that we don't have to keep remembering which is which, and also for a reason I'll show you in just a moment. Okay, so the idea, the question is, does the distribution of mitoses depend on whether the class is cancer or not cancer? That's the fundamental question. And so it's a great idea to figure out the distribution for each of those cells, and as we said last time, Pivot does that. So Pivot does this. For when you do Pivot, the class and mitoses, and the classes form the columns, and you have all the different levels of mitoses here, and you have the counts in each one. And what I'd like to do is compare the two. Why should I not just draw a bar graph of these data? It's counts, and the total counts are different, right? So I have to convert to proportions for comparability. And so this is our old proportions function, and now we convert to proportions. And so I have just applied the proportions function to each of these two columns. And now we have a bar graph, and they have some similarities and some differences. Both of them put most of their mass in the small numbers, but then the blue one has a long tail, which you can't see in the yellow one. So the question is, could that have happened due to chance or not? Supposing you were drawing from the same underlying distribution, could it be that one of them would give you a long tail and the other one wouldn't, just by chance? Okay. All right, so then you need to do something by chance. And here is where the discussion that we had comes in handy, actually. Let's it's worth writing down the two hypotheses. Because what I'd like you to do is look at these, which of these hypotheses is going to have an effect on the choice of test statistic. Well, both of them are, but one of them actually really matters exactly what you're going to do. You should be, when you're thinking about test statistic, p-values and so on, you should be looking hard at the alternative, right? The alternative just says these two things are different. They are distributions, so there's no notion really of a direction of a difference, right? So you're going to have something that includes absolute values of differences, and that's where total variation distance is exactly the right thing to be doing. All right, so we take a look at our data. That's the original data. Under the null hypothesis, you should be able to shuffle this mitoses column and get something that's just a replica. And so we shuffle the mitoses column. So we, okay, let me just, for this once, take a hard look at this line here. So mitosis is this table here. When I do select this column, what do I get at this point? I've got a one-column table. It's not an array. Right? So it's just this table right here. And then I actually I am going to just do it. Because I'd like these pictures to be very clear in your mind, because we're going to do rather a lot of these. So if I just do that up to that point, that's what I get. Yes? I get this column as a table. So because it's a table, I can apply dot sample. Sample works on tables, right? Okay, how many times do I want to sample? The same number. I want to permute the whole lot, right? So what do I put in as a sample size? I'm lazy. I can put in nothing because it'll do that by default. How do I want to sample? With replacement or without? Without, so then that I do have to put in because the default is with. If I do that, right, well, I'll just do it. Any predictions? What will I get? Table, array, which? Table. Okay, I've got a table, and it shuffled the thing. Now, I actually want to work with this thing, and working with tables is a pain. You work much better with arrays, so I am going to select column, and it's got only one column, so it's column 0. Yes? And when I do that, I have an array. And this is 673 however many. Yep. And so now I would like you to please look at this line and just check that that's exactly what has happened there. All okay? Okay. So, and now I'm just giving it a name because I don't want to see all those numbers. So I'm calling it shuffled mitoses. I run that. What's item 0? Well, okay, item 0 was 4 on my particular shuffle. And now what I do is I tack it on to my old table mitoses. And so I have the original ones and the shuffled ones. And the shuffled ones, I'm saying, behave just like the original ones under the null hypothesis. So why don't we look at the bar graphs, the two bar graphs created by this? So actually, so what I'm going to do is create a table called shuffle that has just this class and the shuffled mitoses. So that just looks like that. We've just dropped the middle column there. And now we play the same game. We pivot to this table, and we look at its counts. And that looks like that. So we convert that to proportions, and we look at the bar graphs. And lo and behold, when you have the randomly permuted data, then you can see the tail in both the yellow graph as well as the blue one, which you could not in your original data. So this is a signal that your original data maybe are not quite like random samples, but of course, you have to quantify all this. So far, so good? All right, so now what we have seen visually, we need to be able to quantify, and so we have our function called total variation distance. Everyone recall that function? Yes? Right? It has become such a familiar function now. And so for our original data, the observed total variation distance was about 0.4. And this is a moment which is the same moment every time you use total variation distance in a test. You calculate a total variation distance, and you have no idea whether it's big or small. It's just some number. So to understand whether it's big or small, you need to compare it to something, and you will compare it to what you would get had you sampled at random. And so what we're going to do is look at our shuffled column and compute their total variation distance. And that's about 0.04. So one of them is 0.4, the other one's 0.04. It's about a tenth of what you've got before. So the ones that come from random samples look closer. No surprise, yes? This should be very much the same feeling that we had when we were doing the jury selections. And it should be, because it is. Right? The only difference is how we have generated the new sample. Okay, so we're just going to do this a million times. And so this is just my cut and paste of the previous lines. And we are going to run this again, and we're going to calculate another total variation distance from shuffled samples. And this time, I didn't get 0.04, I got 0.05. Fine, but still quite small. So what are we going to do to make our test? We are going to do this 1 million times, right? Or how much time I have time for in this class. And so there's some code for you to read. Somebody tell me what's happening. First line tells me we're going to do what? We're going to do whatever we just did 1,000 times. Yep. You can choose 10,000 if you wish. I'm choosing something that's reasonable for the time we have in lecture. So we are going to collect all our TVDs. We start with an empty array. Okay, so first line. Shuffled mitoses is what? It is an... Hello? It's an array, right? It's the result of a dot column. It's an array, and it contains what? Randomly permuted mitoses. Okay, next line. Shuffled is what? It is a table, and it contains the original column of classes and your shuffled column of mitoses. And the next two lines do what? The next two lines help you calculate the total variation distance between class 0 and class 1 for your shuffled data. Yes, what does the pivot line do? It gives you a table of the counts. Yes, the cancer group, the non-cancer group, and every one of the 10 mitoses counts, and then you convert those to proportions and apply TVD. And now you've got your new TVD, and then you just do that 1,000 times, and then the rest of it displays the data. So I'm going to run this thing. It's going to take a little while to chug. So take a look at that. Those TVDs, there's 1,000 TVDs in there. Normally we've done 5,000 and 10,000. I just don't have time in lecture. And those are what you would get if the samples were from the same distribution. Those are the results of randomly permuting your data and calling a random group class 0 and a random group class 1. And those go up to about 0.1, but your actual one was 0.4, which is off my screen and possibly in the next building. So what do you now conclude? Like the null hypothesis or not like the null hypothesis? Not like the null hypothesis. The two samples were not chosen at random from the same distribution. In other words, this mitotic activity is actually related to which class the patient is in. Right? If it's a cancerous cell, if it's cancerous tissue, then it has different kinds of mitotic activity than non-cancerous. All right? So very much in the same spirit, indeed very much even execution the same as what we did for juries. We just have to we have to collect the sample of categorized by both class and mitoses. calculate the two individual distributions, and then work out the TVD. That's what we have to do. So I'm going to pause for a second and take questions about code, picture, anything. Okay, so I have a question for you. In our example, the observed value of 0.4 is way outside. Yep. Supposing it had been 0.08, supposing it had been right there, what would we then have done? We would have computed a p-value, right? And how would we have computed the p-value? Just could somebody please remind me? Yes. So you would have calculated essentially a percentile rank in this array of TVDs, and what would you have? What's one way of doing that? I mean, you can certainly use. So my question is, you have to look at some proportion. Yes? What proportion do you look at? Yes? Okay, so value is greater than, are you sure? Okay, the first thing is, if you're going to say greater than, please say greater than or equal to. Yes? You sure greater than or equal to? Not less than or equal to? Now, why greater than or equal to? Because we always do greater than or equal to, because it's the smallest tail. Both of those are the wrong answer. Please don't give them to me. Why greater than or equal to? This is, I'm told you, I'm going to review hypothesis testing. So what do you look at to decide? Yes? And why did I use the absolute value? And why don't I care what direction it's in? Because that's what I said in my alternative hypothesis. It's this that you look at. When you are deciding which side to look at for your p-value, you go to your alternative, right? The alternative just says different. That was what motivated your test statistic to have an absolute value in it. If different, those distances are going to be large. And so the p-value is the chance under the null of getting what you got or something that looks more like the alternative. In other words, something that has bigger distances. And that is why you look at the right-hand side. Terrific. This saves me a bunch of reviewing during RRR week, because we've done it already. Okay. So you'd have 0.08, and then this would be some proportion to the right, and you would compare that to what? Okay, so the number of elements to the right you would compare to the number of repetitions, you'd get a proportion. That proportion you would compare to what? So supposing that proportion came out to be, 2.1%. You would compare to what? I'm sorry? A cutoff, right? Who chooses the cutoff? You do. Yes. Unless I ask you to please use such and such cutoff, you choose the cutoff. But you tell me what you're choosing, and then you make your decision. So if your cutoff was 3% and what you got was 2.1%, what would you conclude? Your p-value is less than your cutoff, so under the null hypothesis, this is too unlikely for comfort, right? So you'll say, okay, I'm just not going to go with the null here, right? Terrific. Okay, so as you can see, there is nothing new about actually doing the test of hypotheses other than how you generate the test statistic, right? Everything else is just the standard form for how to do a how to do a test. So just to capture all this, what I've done is written a function called Permutation Test so that you can use it on any table with any variable in any classes. So this thing takes the name of your table, the name of the variable whose distribution is of interest. So in our case, it was mitoses. So this is a column label. And this is the column label of the two samples, A and B. Right? So for us, it was class. We got cancer and not cancer. Yes? So this is a classic permutation test for A/B testing. And this is how many times we want to repeat. Step 1, find the observed test statistic. We're looking at total variation distance as the observed test statistic. Please take a look at that. Find the observed TVD. Good? Any questions? Okay? Right. Next step. Do the actual permutations and the test. All right. Take a look, please. You should just see it as a collection of stuff we have done already, where we were writing mitoses, we are now writing variable. And where we were writing class, we are now writing classes. Yes? The empirical p-value is what we just discussed. Take your, find the proportion of your total variation distances that are greater than or equal to the observed statistic. By the way, on your midterm, there was a question like this. There was some question about whether assigning people Mondays, Wednesdays, and Fridays versus Tuesdays, Thursdays, and Saturdays was like tossing a coin. Yep. And in the end, there was a question of how do you find the p-value? And you had to write essentially a line that looked something very much like this. That was perhaps the worst done question on the midterm. Because people didn't know whether to look at the left-hand side or the right-hand side. Right? So when you are making that decision, please go to the alternative. Check that your test statistic is consistent with that, and that should tell you. All right, so here's a function, and so once we've got a function, what we're going to do is we're going to use it to see if the variable bland chromatin is related to whether the person has cancer or not. And this I can run and have it go. While it's going, I can scroll through the code and take any questions that you have about the code. What's the purpose of it? That looks like a ton of code. What's the purpose of it? To test whether two samples come from the same distribution or not. And so in other words, if you go to just Google A/B testing, right, then you will get a ton of websites that offer for a fee to do the A/B testing for you. Right? So they will tell you how to set up your sampling, and then in the end you'll have sample A and sample B, and then they tell you don't worry about it, we'll give you the result of the A/B test. So you are the people who will create the result of the A/B test. So you'll have a table of data, and there'll be this variable that will be labeled as A and B, and you will run this line of code, and you will get the result of the A/B test. And that's what we got for bland chromatin. So for bland chromatin, under random sampling, the total variation distance should be up to about 0.2 at biggest, but the actual one was 0.77, so bland chromatin appears to be related to whether or not the tissue is cancerous. Good? Yes? My entire function did not have a return statement because it is not giving me back something that I'm going to work with. All it is doing is display. All right? So if I actually want to work with this observed TVD, I would have to return that number, right? But this is just a picture on the screen. That's all it's doing. That's why it doesn't have a return statement. Okay. So what I'd like to do now is go back and well, no. We have two categorical distributions. We know how to compare them. I'm now going to move to numerical distributions. When you have numerical distributions, so if you look at weights of one group versus weights of another group, then how do you compare the two? You could compare two histograms, but then you would have to decide what the bins are. Right, and depending on how you decide what the bins are, you would have different shapes of histograms, and, well, then you get into issues there. So what we've done typically is we've just compared the means or the medians. Right? If you have numerical distributions, you have summary statistics that you can use. And for this, I want to go back to a place where we actually had a random sample drawn from a population, I would have loved to give you an actual A/B test data from a website. But we have a little issue in this class, is that we're trying to be so public. We post all our data on the World Wide Web. And those kinds of data are usually proprietary, and even though people might think it's fine to use for educational purposes, when we go and put it on the World Wide Web publicly, they're not so happy. So I'm still working on getting an actual data set, some kind of maybe slightly jittered data set that somebody is willing to release. For now, what I'd like to do is I'd like to go back to these sampled people, the mothers and babies, and we've looked at these variables. But the point of the study was this one. The point of the study was, does smoking during pregnancy influence the baby? That was the point of the study. And the key question was, one of the key questions was, does smoking affect birth weight? Because smaller babies just have, a few more problems than larger babies. So the issue was the relation between smoking and birth weight. So I've just reduced the table to that, and the question is, does the weight depend on whether smoking is false or true? First, they're not the same number of each kind. There were 700-something non-smokers and 450 smokers. And for the non-smokers, the birth weight distribution looks like this. And for the smokers, the birth weight distributions look like this. And so if you look on the horizontal axis, they're both somehow centered kind of like around 120, but kind of bell-shaped. And the question is, are these two drawn from the same underlying distribution or not? Right. And you're looking at that going, I don't know. This one looks kind of narrower, and it looks kind of shifted over to the right compared to this one, but maybe it's could have happened by chance. And so what we're going to do is we're going to run our permutation test. Yes, we're going to take all 1,174 birth weights, and we're going to randomly shuffle them. And we are going to call 715 of them non-smokers, so basically Class A, and 459 of them Class B, and then we're going to find just the difference statistic. I'm just going to use the difference between the means. Okay. So step one is to find the difference between the means of my two groups. Okay, so I'm just reminding you a little bit of, you've got the smokers and non-smoking column, and you've got the birth weights, and the group was set up for finding statistics to do with different groups. So you group the thing and you provide the mean as your computation to be done. And what you get returned is a table that gives you the means of the two groups. And what you can see is in your sample, the non-smoking mothers had slightly bigger babies. Those are ounces. So smoking seems to be associated with, on average, lower birth weight. But, of course, all of this could have happened due to chance. One of the things that I'd like, so we can, of course, take, subtract. I mean, we can see it's about 10. The reason I have written out, you can see it's about 10. The reason I have written out this code in some gory detail is we are going to want to program in a function that just does this, and so we have to know how to find the mean, and then how to find the difference between the means in general. Now, the way I have written this, clearly I'm doing 123 minus 113, and that's a positive number. You could have done 113 minus 123. You'd have got minus of what we got. The hypothesis that we are going to test is the two distributions are the same versus the two distributions are different. What should your test statistic be if I'm going to use means? Same, different. Your test statistic should be mean 1 minus mean 2 absolute value. Yes, because you're just saying different, you're not saying in which direction. Okay. Now, the way I did it, by just happenstance happen to get a positive value, but in general, I would do the absolute value of the difference between the two means. And that has to do with my alternative. So my observed difference is that. Okay, so we're going to write a permutation test function. Step 1, boil your table down to the two things that you need. You need your variable, and you need the variable that has your sample A, B. Yes? Okay, next, find the observed statistic. Could you take a look at these two lines and recognize that the first line is doing what? It's grouping your data and finding the mean of the two groups. The second line is subtracting the two means by extracting the column and doing item 0 minus item 1, and then taking an absolute value. Okay, so then you go ahead and you permute. Under the null hypothesis, you can permute the whole lot. What are you going to permute? You're going to permute your variable column and extract the permuted data. You're going to tack it on to your classes column. This is what we just did. And then you're going to calculate the statistic for your new thing, and then you're going to tack on the statistics, and then you're going to do a p-value and a display. And so I will leave that up there. I'll give you a minute to read that and convince yourself that it's the same code as before, except for how to calculate the test statistic. And if this is feeling very slow and very kind of, yeah, move on, that's exactly how it should feel, right? You're doing something that is on every website as, well, for A/B testing, you need to understand this, and this. Yeah, fine, you get it. Okay, so no drama here. We're going to run a permutation test to see whether smoking and birth weight are associated. Yep, and I'm just doing 1,000 of them just because there's 1,100 or 1,200 babies and it takes a while. Right. Do you see the shape of distribution? Why is the shape of distribution like that? Because you have that absolute value in your statistic. Half of a bell. You've seen this over and over and over again. Yep? Okay. So if the null hypothesis were true, then the difference between the two means in absolute value should range somewhere in the 0 to 4 range, but our actual difference was 9, so what's your conclusion? Your conclusion is that the two, it doesn't look like random samples from the same distribution. Yes? So smoking and birth weight are associated. That's your conclusion. And this is exactly like we did before. It's just different, absolute difference in means other than total variation distance. But this leaves me a little bit, it leaves us with a question. So you're saying that these women who smoked, their babies were on average somewhat smaller. The natural question, if you're a medical person, is, well, how much smaller? Because I need to do something for these children. Yes? And so here, answering this question simply by yes, no, they look the same, no, they don't look the same, is actually unsatisfactory. What you want to know, really, is what's the difference between the two means? How big is the difference? Because that's what you're going to use as a medical person to treat the babies. And therefore, now the question that was raised at the beginning of the class, where you sampling with replacement or without replacement, comes into place. Because what you'd like to do is not have any hypotheses at all. They're drawn from the same distribution. They're not drawn from the same distribution. Forget the hypotheses. Just estimate the difference between the means. So for our particular sample, we got 9.27, right? Had we drawn a different sample, we'd have got a different difference of means. Yep? How can we come up with a different sample? The bootstrap. Yes? No hypotheses, no nothing. Just generate a copy of the sample that you already have. You bootstrap. You bootstrap the sample, then you'll get a bunch of smokers and non-smokers and corresponding birth weights. You can find the difference in means. And then you do it again and again and again and again. And at the end, what will you do? So supposing I have 10,000 of these differences in means, what are you going to do? confidence interval. You are going to use the middle 95% of them to estimate the actual difference. And so we're going to carry that out. It's straightforward to carry out, but the thing that you should take away from this is when you are comparing just two numerical parameters, like two means or two medians, maybe don't do a hypothesis test and just say different, not different. Go ahead and simply estimate the difference. Yes? The empirical p-value is 0 because the 1,000 total variation distances that we computed are all in the 0 to 4 range. Ours was 9.2, right? So none of them was greater than or equal to 9.2. The true p-value is very close to 0, not exactly. All right, so what we're going to do is here's a function that does a bootstrap confidence interval for the difference between the two means. So you compute the difference between I don't want an absolute value here. I'm going to drop the absolute value. I just want to see the difference, and I actually want to know whose babies are heavier. All right, so please understand, I am not testing any hypotheses now. I'm just seeing which ones are heavier and by how much. So I'm just looking at mean 1 minus mean 2. You could look at mean 2 minus mean 1. Your confidence interval would be minus of mine. And so now we bootstrap the sample. Please note, what's the difference between this and what we've done before? Table.sample, what's the difference? It's with replacement. Yes? And there is no null hypothesis, there is no permutation, there's no nothing going on. You are just computing the difference between the two means. And while that's running, I'll leave that up. Is it clear why I dropped the absolute value? Yes, I'm not testing same versus different. I'm just saying how different are they, and it matters to me which one's heavier. Right, and the absolute value was getting rid of that information. So here we go. Difference between the means. What we're estimating is that in the population, that difference is between 7 and 11 ounces, roughly. That's actually a helpful result. The women who didn't smoke, their babies were 7 to 11 ounces. That's, half a pound or more heavier than the babies of the women who smoked. And that's something that a doctor can use. Okay? There is something you can do. Take a look at that. Do you see a 0 in that interval? No. So if you were to test the hypothesis, the difference between the means is 0, what would you end up with? Would you conclude the difference is 0 or not? You would conclude not, because your confidence interval is going from 7 to 11. So you can use this confidence interval to test your hypothesis that you had before. But this confidence interval does better. It actually tells you what is the difference. And so now that we've got a routine, we can run it to see were the ages different for the smokers and non-smokers. And if they were different, then how different were they? That's actually a question to which I didn't know the answer. I didn't know who was going to be more represented in the smoking group. And if I look at the difference between mean age, that is going from here to here, just over 0 to about 1 year. Yep. And so if I look at, we are doing non-smokers minus smokers. Yes, so non-smokers minus smokers, the confidence interval is like this. So who's older? Excuse me? Non-smokers are older by a tad, right? The 0 is hovering real close. Now, what your instinct should say absolutely shouldn't matter is the height of the person, Whether they're a smoker or a non-smoker, the height of the person shouldn't really matter. And we sincerely hope that it doesn't. Let's just do this. So is smoking related to the person's height? We'll run this thing. If that confidence interval doesn't have a 0 in it, I'm going to be very upset because something weird is happening. I don't know. So, and aha. Okay, if you're testing for a difference and your confidence interval changes sign, goes from minus to plus, then there's a 0 in there, right? That means you don't have enough to say that there's an effect. All right, guys, I hope you have a great Thanksgiving break. I am going to give thanks for the privilege of working with such a nice group of people. I'll see you next Monday.